Hello, everyone. Welcome to another brief lecture for Phil 115 Critical Thinking. This is chapter 4, Deductive Argument Patterns. So the nice thing about this chapter is it focuses just on deductive reasoning. And one nice skill that we're able to take out of this chapter and to make us better critical thinkers is to be able to recognize the kind of argument form that someone else is using or that we might use ourselves. So it's about recognizing patterns, recognizing arguments, and knowing which ones are good pieces of reasoning, that is, which ones are valid and which ones are invalid. So that's the main focus of chapter 4. So I think it's very fitting to have a nice reference to Spock here from Star Trek. He was Mr. Logic. So I think there are always good reasons to learn some elementary logic, even if it's to make our own thinking clearer and sharper. So again, just to review from chapter 3, if we have an argument, remember they come in two types, deduction and induction, or deductive reasoning and inductive reasoning. So it's going to be one of those two. If we're talking about successful arguments, in deduction, they're either valid or invalid. The successful ones are valid, that is, they have the right structure or form. And if they don't guarantee the conclusions, then they're invalid. For inductive reasoning or inductive arguments, they're either strong or weak. Then we ask, does it have true premises? So a deductively valid argument with all true premises as well as a true conclusion are sound. If it's invalid, then it's unsound, or if even one premise is false, then the entire argument is unsound. For inductive arguments, they're either strong or weak, but all strong arguments with all true premises as well as a true conclusion are said to be cogent, and if that's not the case, then they're uncogent. So I hope this this flow chart, is at least somewhat helpful to us as we really think about arguments and how we assess them. So as I've been hinting at, to be good at evaluating arguments, it's important to be familiar with argument patterns or forms, the structures on which the content is laid. So knowing some common argument forms makes it easier to determine whether an argument or a piece of reasoning is deductive or inductive, and whether it is valid or invalid by consequence. Most of the argument forms we will cover here in chapter 4 are what we call syllogisms. This goes all the way back to Aristotle, one of the first philosophers and logicians to give us a systematized set of rules for reasoning. And a syllogism is just a fancy term for any argument, any deductive argument made up of 3 statements, 2 premises and a conclusion. So most of the argument forms we'll learn will be syllogistic reasoning. So some of the most common argument patterns that we encounter even in everyday life contain conditional statements. We use these all the time. These are the if-then statements that we use. If it's sunny, then I'll go outside today. We use conditional statements as standalone statements, and especially we use them in arguments. So simple example, if a job is worth doing, then it's worth doing well. So the first statement in a conditional premise, the if a job is worth doing part, we call that the antecedent. The second statement, the then it's worth doing part, is known as the consequent. So a conditional statement, therefore, has 2 parts, the antecedent and the consequent. And hopefully that's somewhat intuitive because we think the consequent or consequence almost sounds like it follows from something else, which it does. In a conditional statement, it's the antecedent. So please make sure and remember which part is which in a conditional statement. And then sometimes we'll have syllogisms that have very specific names that have conditional statements, and we'll talk about that in just a moment. So since argument forms are structures distinct from argument content, we can easily signify different forms by using letters to represent statements in the arguments. This is a pretty common convention, not just in logic, but also in math, in science, where we use variables or things to stand in place of other things. So for example, let's look at this argument. If it is sunny, then I'll go to the park. It is sunny, therefore I'll go to the park. Now we can represent the pieces of this argument with P's and Q's. We could also use A's and B's, F and G. Any letter really would work here, or a set of letters would work to stand in for the sunny part and go to the park. But notice that this argument has this form: if P then Q, P therefore Q. So we'll know that that is a specific argument type, modus ponens, which is always valid. It always has the right structure. So it's if P then Q, or if A then B, A therefore B. Or if we're using P's and Q's, which is common in the book, it would be if P then Q, P therefore Q. So what's an example of an argument that takes that form? If I finish reading, then I can play Xbox. I finished reading, therefore I can play Xbox. This argument is always valid. It's never invalid, no matter what I plug in for P and Q here. Now, careful, it doesn't mean it's sound, right? It could be something really ridiculous. It could still have the right structure, but be unsound because of one or more premises being false. Modus tollens is also always valid. This is outlined in the book. This has the following form: if P then Q, not Q, therefore not P. So an example would be something like, if it's raining, then the park is closed. The park is not closed, therefore it is not raining. So modus ponens is always valid, as we just said, and modus tollens is also always valid, and we can prove that in a symbolic logic class. But these are two of the most common deductive argument types. So that's why I think, agreeing with our textbook author Vaughn, I think it's important to know some of the big names of deductively valid and invalid argument forms. This one, I think, though, is probably the most common that we use in everyday life. This is called a disjunctive syllogism. We call it that because it's got a disjunction in there, which is an either or statement. It's also always valid. So it's something like either P or Q, or either A or B, and then you dismiss one of the options, and so you're left with the other option. So either P or Q, not P, therefore Q. It could also be this. So it could be not Q, therefore P. So simple example, either Joe Biden or Donald Trump won the US election. Donald Trump did not win the US election, therefore Joe Biden won the election. This is always valid reasoning. Hypothetical syllogism, a little less common, but we do use things like this, like chain reasoning, where we say, if this thing is true, then it leads to this. And if that thing is true, it leads to this other thing. So we do use that somewhat regularly, I would say. It takes the form of something like, if P then Q, if Q then R, therefore if P then R. But we could use A, B, and C just as well here. If A then B, if B then C, therefore if A then C. So here's a silly dramatic example. If Anthony drinks lead paint, then he gets violently ill. If Anthony gets violently ill, then he goes to the hospital. Therefore, if Anthony drinks lead paint, then he goes to the hospital, right? Don't drink lead paint. But you see how this thing leads to this thing and it leads to this thing, right? That's called hypothetical syllogism, and that's also always valid reasoning. Okay, so disjunctive syllogism, which we talked about. Here's another example. I think we use this for choices all the time, whether it's, trying to figure out directions. Either we take I-5 or Highway 99 to get to Seattle. We can't take I-5 because it's closed, so we'll have to take Highway 99. I think that's pretty common reasoning, or the kind of reasoning that we use on a regular basis. And then hypothetical syllogism, right? If A then B, if B then C, therefore if A then C. So both of those are valid. Less common one is known as constructive dilemma. It has a slightly more complex form, but it's still valid, and we use a form of this every so often. It looks like if P then Q, and if R then S, either P or R, therefore either Q or S. So here's an example. If we get a cat, then there will be fur balls, and if we get a dog, there will be fleas. Let's say we're at the rescue shelter. Either we're here to get a cat or a dog, therefore we're either going to have to deal with fur balls or fleas. An offshoot of that is what's called destructive dilemma. It's slightly different than a constructive dilemma. So it's if P then Q, and if R then S, then neither Q nor S, therefore neither P nor R. So it would be very similar. So if we get a cat, then there will be fur balls. And if we get a dog, then there will be fleas. We will neither have fur balls nor fleas. Therefore, we're not going to get either a cat or a dog. Okay, so one of my favorite pieces of reasoning to talk about, and this is incredibly important for those of you going into any scientific field, and especially criminal justice and law students know about this argument strategy. It's called reductio ad absurdum. And this is a very famous kind of reasoning, and it's quite common in some of the most cherished scientific literature and math literature. Some very famous people use this argument strategy, and we use it every day in courtrooms across the country. So it's essentially, well, as the name implies in Latin, it means reduced to an absurdity. So essentially what we're doing here is we assume somebody else's position and we show that it leads to an absurdity. In other words, if we accepted that view, then it would lead to this absurd thing, which we can't accept. So therefore that view is not correct. So we do this all the time, like I said, in courtrooms and also in science. So it has the following form. So we assume, let's say P, some statement, let's assume it's true. Well, if that's true, then it leads to Q. So if P, then Q, but not Q. So therefore not P. So this should remind you of modus tollens here, but the important difference is we're assuming something. We're assuming that P is correct, and we show that it leads to an absurdity. So we thus ultimately reject that position, call it P. So here's a simple example. Let's suppose you met somebody and they said, water cannot freeze. Okay, well, let's assume that. Let's suppose that water cannot freeze. If water cannot freeze, then ice can't exist. But you show them some ice, right? But obviously ice does exist. So therefore water can freeze. So notice how we've ultimately rejected that position. We started by assuming P. We showed that if we accept P, then it leads to this, but that's clearly unacceptable because ice does exist. So therefore P is not the case. So again, the strategy is if the contradictory or negation of a statement leads to an absurdity or falsehood, then the negation of the statement is false and the statement itself must be true. So as such, reductio always begins by assuming the opposite of what is meant to be shown in the conclusion. So by demonstrating that this assumption implies something unacceptable, one can then refute it on that grounds. So again, this is why it's incredibly important for lawyers to use this strategy, because we can imagine cases where a lawyer might say, the prosecution has argued this, but if that is the case, then we would have seen or expected this, which we never got. So the prosecution's case has no merit, or the defense's case has no merit, right? You're showing that you're taking somebody else's position seriously, but that if we do so, it leads to this absurdity, which we cannot accept. Thus, the overall position is untenable or unacceptable or false or something like that. So here's an actual example of reductio being used in history, in the history of science in particular. This is Galileo, one of my favorites. And here's me at the Leaning Tower of Pisa. So Galileo supposedly did some experiments at the top of the tower. And one of the things that he is credited with is refuting Aristotelian mechanics, or the idea that heavier objects fall faster. So Galileo is often credited with being a philosopher and scientist who helped us move along to a different model of physics that culminated with Newton in his celebrated mechanics. So Aristotle thought, understandably, that heavier objects fall faster to the center of the earth. So Galileo, I'm oversimplifying this quite a bit, but the idea is still there. So he goes to the top of the Leaning Tower, and he's supposed to be doing these experiments. So he says, all right, Aristotle, let's suppose you're right. Suppose that heavier objects fall faster to the center of the earth. Well, if we drop two cannonballs of unequal mass from the top of the tower here, if you're right, then they'll hit the ground at different times. So Aristotle, if we accept your view and I drop these two cannonballs and they weigh differently, then the heavier one should hit first, right? But what happens when we drop the cannonballs? They don't hit the ground at different times. They roughly hit the ground at the same time, right? So what do we conclude from that? Well, therefore, heavier objects do not fall faster to the center of the earth. So this is meant to be a very famous refutation that Galileo performed by doing these experiments at the top of the Leaning Tower of Pisa. He also did it with another of Aristotle's views, the view that heavenly objects are perfect. So Aristotle thought that the closer you are to God, the more perfect you are. And naturally, things in heaven are going to be heavenly, right? So that's why heavenly objects were supposed to be perfect, or more perfect than the earth. So they weren't supposed to have any imperfections, right? Well, suppose that that's true. Galileo is often credited with developing the telescope, not creating it, but developing it. And he did a lot of observations on the moon and discovered some moons of Jupiter that we name after him. So let's suppose that heavenly bodies are perfect, Aristotle. If heavenly bodies are perfect, then we shouldn't observe any deformities on their surface. But what happens when we look at the moon? There's lots of craters and deformities. So therefore, heavenly bodies are not perfect. So another good example of reductio ad absurdum. So we'll close by talking about a couple of invalid argument forms. They can have a structure very similar to valid argument forms. However, their conclusions do not necessarily follow from their premises. So the first one is denying the antecedent. This one is always invalid. So this has the following form: if P, then Q, not P. So we're denying the antecedent, which we know what that is now, right? The antecedent is the first part of a conditional statement. So if P, then Q, not P, therefore not Q. So here's a good example. If Albert Einstein invented the polio vaccine, then he was a great scientist. Albert Einstein did not invent the polio vaccine. Therefore, Albert Einstein was not a great scientist. So notice here that it's true, Albert Einstein did not invent the polio vaccine, but from that, it doesn't follow that he wasn't a great scientist, right? So there's something wrong with the form of the structure here, that even if the premises are true, the conclusion could still be false. And by definition, that can't happen in a valid argument. So denying the antecedent, whatever you plug in for the P's and Q's here, it's always going to be invalid. Affirming the consequent, also invalid. So this has if P, then Q, Q, therefore P. So here's a good example. If Seattle is the capital of Washington, then Seattle is in Washington. That would make sense, right? If something is a capital of your state, then that place would be a city in your state, obviously. Seattle is in Washington, which is true, right? Therefore, Seattle is the capital, right? Now, so there's something wrong with the way this is structured. So premise one says if P, then Q, but just because it's a Q doesn't mean it's a P, right? So this argument form is always invalid. So we just talked about denying the antecedent. Here's another good example of denying the antecedent. If Anthony is a father, then he is a man. Anthony is not a father, therefore Anthony is not a man. I can still be a man and not be a father, right? And affirming the consequent. If Anthony is a father, then he is a man. And just because it's true that I'm a man, does it mean that I'm a father? No, right? So both of these argument forms or pieces of reasoning are always invalid. So that's why it's helpful to know the names of these. We can even spot them when other people are using them and maybe gently tell them to not use invalid argument forms, right? Okay, so I'll skip the practice for now. We can do this hopefully together at some point. And then if you have any questions about argument forms or their names, please be sure to let me know. And thanks as always for listening. I'll talk to you soon.